we have a new quantity to define, and this is current. And note that we're going to call this conventional current to distinguish it from electron current, but typically we're just going to refer to this as the current. Here we use capital I. And be careful to make it clear that this isn't 1 or L. This is a tricky thing with handwriting. And this is going to be the rate of charge flow. Note that we're not saying electron here, we're saying charge. And so this is going to be, if we look at one point, we're looking at how much Q is passing that point in a certain amount of time. We are defining it as a derivative, and there's going to be good reasons for this, but frequently we're going to get to talk about constant current, which means that this just becomes delta Q over delta T, but that's only if we have a constant rate. Once we have that, we can obviously rearrange and get this new equation where you can think about this as delta Q or just Q. So this is just a definition, again, a definition of conventional current, which is going to be charge flow. Note that we are going to be defining this as positive charge, which will make this a little confusing. So what are the properties of current? First, the units we use are amperes. What everyone says is just amps. I have 1 amp of current. Very few people would ever say I have 1 ampere of current. If you say that, I'm probably even going to be confused. So we call these amps, even though technically the unit is an ampere. We abbreviate it capital A, and this is just a coulomb per second. So if you imagine a normal ceiling light, and this is tricky in that this is certainly true for incandescent lights. If you're talking about a LED light, this isn't quite true anymore, but it uses about 1 amp of current, or we would say draws 1 amp of current. For things like calculators, flashlights, anything running off batteries, any small electronics, we're typically talking about milliamps, so that's thousandths of an amp. So you should expect in some calculations to get maybe 1 or 2 amps. If we're talking about household things like stoves, refrigerators, those might use, say, 5 amps, 10 amps. But if we're talking about a small device or circuits, we probably only want to get milliamps. It's possible to get microamps, though that's really difficult to measure. If you're getting thousands of amps and we're not talking about powering a city, you should probably be a little concerned. So now let's compare and contrast between conventional current, this new idea, and electron current, which we talked about in a previous video. Note that their symbols are different. For conventional current, we use capital I, and for electron current, we use lowercase I. And I add sub e, since 1, I can be square root of -1, and 2 to just remind you that this is electron current. So both of these relate to charge divided by time, but conventional current is literally just charge divided by time. And note that once we're writing it this way, we are assuming that this is a constant I, right? Remember that you need to use the derivative in any situation that is not constant. So it's whatever charge you're talking about. Here, this was just basically the number of electrons, right? So be careful in that this is the number of electrons here. And so to just go between them, all you're doing is you're multiplying the charge per electron, which is E, times the number of electrons. So conventional current is just E, the charge on 1 electron, times your electron current. Pretty simple. That's the relationship. Normally we talk about conventional current. When we talk about electron current, it's usually when we're thinking about a microscopic model, so just keep that in mind. Now let's talk about direction. Current it's kind of a vector. We don't normally write it as a vector, but it does have a direction. Conventional current is defined to go in the direction of the flow of positive charges. Now, yes, electrons are actually the charge carriers, right? If we look at this picture, you should get a little upset because we're showing our positive charges moving. And that's not what happens, electrons move. However, this is the model for conventional current, which would also be going to the left. What's nice about this is it then matches electric field, which is going to the left. So if we think about this as a vector having a direction, is parallel to our electric field. but we then have to actually talk about positive charges. If we want to think about electron flow, right? Electron flow is the opposite direction. And another way to think about this is we said that conventional current is equal to E, the charge on the electron, times our electron current. But if we really just thought about Q, the Q of an electron is negative. So that's part of why we end up with an opposite sign here. So in this picture, electrons are flowing to the right, which is the direction the force from the electric field would cause them to go. But we actually say that our conventional current is to the left, which corresponds to positive charges flowing to the left. If for whatever reason you go on to study electronics in the future, you will find that some electronics textbooks will use conventional current, which is what we're doing, capital I, and other electronics textbooks will sometimes use electron current. And basically, the reason that we have this difference, that electrons are actually our charge carriers, but they're going to the right, and we'd say that current is going to the left. This is just due to history. And this is due to these ideas being defined before physicists fundamentally understood what was going on. And so even though electrons are the important thing zooming around, they were given a negative charge, again, just by convention. So this is confusing and some people are trying to fix it, but then it makes it more confusing because then you have two different conventions. So for this class, and again, there's a chance that this is different from how you've learned it in the past, we talk about positive current, the direction of current flow, to be in the direction that positive charges would be going, and we know that that actually corresponds to electrons going the opposite direction. There is one more quantity to define, and we're not going to do very much with it right now. It just comes up in certain types of problems in a derivation we're going to do later. Oops. And the idea here is current density. And this is a mistake. This should be lowercase I. Sorry about that. Lowercase I. So current, we said, was our charge of the electron times our electron current. And before, we knew that electron current were these three things multiplied together got you electron current. Well, if you notice, we have A, which is just the cross-section of a wire. And what we want to try to separate here is our specific conductor, the specific wire we're working with, from like bigger picture properties like the electric field, or what we're soon going to see is the potential. And so we can actually just divide out A to get what's called current density. So J is used for current density. I don't know the origin of this, probably because it's a letter like I, but different. And this is then, again, just defined as our number density of electrons times the charge, fundamental charge of one electron, times the drift velocity. And in a future video, we're going to relate this to some other quantities. But just know that all current density is dividing out the cross-sectional area of whatever object the current is flowing through.